Okay, welcome back. So I know that it is the 10th week in the course, but this says 9. It's because we skipped a week, but that's fine. Today, we're just going to go through now adapting what you've learned so far to longitudinal data. So a lot of this is just duplicate from lecture. I'm just going to kind of go through some things that change a little bit, and you'll see that it's really not a lot, just kind of thinking about where observations are clustered. So this is really where mixed effects models have shined a lot, and really where the development kind of accelerated from was in alternative to the classic repeated measures approach to longitudinal data, which was very restrictive. There's still, assumptions that we have to fulfill with a linear mixed effects model, but one of the things that is nice is often in real world cases, there we don't always have the same number of observations per person in a longitudinal design. We will in this example, and in most of the examples we'll use in class, because real world longitudinal data is actually hard to get your hands on, but you may know, if you've been involved in any perspective study or anything like that, that dropout is common. So if you are checking in and measuring something over and over again over time in the same set of people, it's often the case, unless you're paying them a lot of money and they're somehow captive or something, you're going to have times in which you miss people, they drop out, they come back, so on and so forth. All of those things are not an issue with fitting mixed effects models to longitudinal data sets. So here's an example of data that comes distributed with the LME4 package. It's a very simple experiment. And before we talk about it, I'm going to talk about the terminology that you'll often hear when you use data like this. So I often call it long data as opposed to wide. The tidyverse folks call this tidy data. And so it's called long as opposed to wide because it's in what we call person period format, which means that we have the data, each row identifies a unique observation at a certain point of time for a certain person. So the data set here, which comes from a study on sleep deprivation and cognition, is that each row identifies reaction time, and I'm not sure what task they had them do. This is pretty short reaction time, so it might have just been like a recognition task. This is in milliseconds. The days variable now records which day of the study is it on, and in this case, a 0 is in there, which means it's the first day or baseline, and that's often a coding system that works well, is to have the first observation of a participant or a person or whatever it is coded as 0, and that's really the focus actually of this week and the homework. And then we have a new grouping factor, which is the person or subject themselves. So we see that this is all of the data, or at least the first 6 rows from subject 303. So in fact, if we scroll down, this is pretty common from cognition and lab-based experiments. We don't have that many people in the study. There's no explanatory variables in this data set. Simply it's just there to illustrate a sort of single level random effects structure. So observations are clustered in people. We can visualize it using the XY plot function. This is in the older lattice package. And so we can see we actually have balanced data. So there are should be 10 data points for each person, days 0 through 9. And we can see all of them. So everyone in this case does actually have the same number of measurements. because this was a laboratory study and people were paid, easy to do. Again, if you're doing something in the wild, where you're following up, with a cohort, you might not have this balance. But the XY plot um, function, you can do this in ggplot as well. XY plot was sort of made for this. You have these panel plots, which is, this is each participant broken out by themselves. And, if you look at it, you can see, some general trends, although you also see some variability in those trends over time, right? And so that's what we're going to be interested in, just as usual. We might like to know, is there an overall trend? Does reaction time, for example, the hypothesis would be that, sleep deprivation slows cognition, right? So slower cognition means slower reaction time when you have to recognize letters and numbers or something like that. Very simple experiment. And so we can see generally that's true, but with some variability. So, subject 309, for example, seems to be pretty immune to sleep deprivation. This person is one of those lucky ones that maybe that doesn't have to sleep that much. Note we also have, some nonlinearity. So 352 this is much more of a kind of an exponential flattening. So some real degradation of response time followed by kind of a plateau, right? So, classic mixed effects models. We want to allow some variability, not only in where people start, so their baseline reaction time, that's intercept in this model. We'd like to allow for some of that variability, but more importantly, we'd like to also allow for some variability in the slope for days or time in this case, right? So we'd like to, and we're just going to fit linear models, but we can test some nonlinearity as well in there, and I'll show you how to do that. So first step, nothing really changes, except for now we are at a different level. So, you know, basically, again, we can answer these questions about whether it's linear growth, could we add a quadratic term, and then is there variation in slopes and intercepts, right? So in Raudenbush and Brick, they change the notation a little bit, which is, kind of a little bit weird, but all they do here is we assume that at level one, which is now the day per subject, so time t for subject I is a function of some intercept for subject I, the slope, and then the random error at the subject level. And we allow for time to be differenced by a lag. Okay? Now, at this point, in the way this data set is set up, L is just going to be 0 because we don't want to move time around. We've got it recorded pretty well. But if you have time recorded in months or, in some other time, you could subtract, or again, for homework, you'll explore what happens when instead of trying to model. So what does this do, right? This allows you, again, to center the data differently, to move the intercept around such that as it is now, the intercept is going to estimate the variation, or the intercept variation is going to estimate the variation at the beginning of each participant's data, because that's where 0 is, right? How do we get to just intercept? This has to be 0. So boom. Right? Level 2, we're not going to, at first, we're just going to let the intercepts vary and keep the slopes fixed. And so our combined model is going to have just one fixed effect, the effect of time, and then 2 random effects along with, just 2 random effects, no correlation. Right? So we do everything the same as before. Right? Boom, same code. Reaction time is our dependent variable, days is our time variable, and now subject is our clustering variable. And so if we fit this model and we look at the results, we're going to see something very similar. Here we've got our intercept variance, it's pretty substantial. On the standard deviation scale, right? It looks like there's quite a bit of variation, 37 milliseconds. That's a lot. And we can see here that, yeah, the linear effect of time also seems to be substantial, right? As a linear relationship on average, pooled across the subjects, we're estimating about a 10 millisecond increase for each day of the experiment. As before, we could calculate the interclass correlation, whatever we want, and then we would go about adding more variables to try to explain some of these relationships here. The tricky part is a lot of times, we may have measurements along with time. So, let's say we also, gave them, caffeine, some dose of caffeine on these days. That would be called a time varying covariate. We can handle those in these models just fine. It just, the interpretation can be a little bit wonky. So we won't go over that in this course. It's similar to the way you have to deal with time-dependent treatment and exposure in survival models. So we'll just leave that for a different class. So again, nothing is different. It's just the data that have changed, and sort of the way you have to think about them. Model comparison and testing also works the same. We could use confidence intervals with the bootstrap, and so we could make some inference about our intercept and slope. We can see that both we wouldn't expect little sigma to be 0, but we can see that the variance in the intercepts is clearly much different from 0, and such that we would want that term in the model. We almost have to. Our design calls for some way to take into account that these are repeated measures across participants, right? So before we talk about model comparison, we have to have a model to compare to. So we're going to add now, keep with the equations we had above, right? And now add a random effect for slope. So now we will allow the slopes to vary across individuals, look at the degree of that variation, and then do a likelihood ratio test of the need for the new variance parameter in there. Now note, this likelihood ratio test is going to have 2 degrees of freedom, because when we add a random effect for slope, we sort of by default add in a second variance in that matrix, the covariance between the intercept and the slope, which is sometimes a helpful thing to have in your model. It can help you diagnose different things. So just like the last tutorial, to allow different participants to have different slopes in their individual models, which is what we already see here. So effectively what we're doing is we're fitting a regression line to each participant individually, and then pooling those results, and then asking, is there substantial variation in those slopes? We just add the independent variable that we'd like to ask that question about over into the random effects side. Now we're implicitly adding a 1 in there. If we don't want the intercept to vary, which you kind of have to have a lot of reasons to not want that to happen, unless there isn't an intercept in your model, then you would essentially, there's a 1 in there, so you're going to have random intercepts. Now, in the book, it talks a little bit about the likelihood ratio test issues. It turns out that for testing, using the likelihood ratio to test random effects, that test ends up being conservative, meaning that it's, the p-value is that you get is essentially going to be essentially like a lower alpha level test. Um, so what that kind of means is if you use a likelihood ratio test to ask the question, do I need random slopes in my model? And you get a result like this, where your P is very, very, very low. You're usually pretty good. And in fact, we can see on a number of the criteria, right? The model with the random slope has a smaller AIC. Its log likelihood is larger. Um, and so, it's a pretty large chi-square. With 2 degrees of freedom, the approximation is pretty okay. Um, and so we could be confident with that. If we want to, if we really want to be, thorough, we could try the parametric bootstrap. So remember, what the parametric bootstrap is doing is it's we take the model that we're interested in, and we essentially resample a null model and run a number of likelihood ratio tests, and then basically we figure out how many of those were significant, and we put that out as the p-value. So the result there is not too much different in the way that we would make our decision than the likelihood ratio test. It's a different statistic in p-value because what's happening here is slightly different from the naive approach up there. But we can see that the the uh, uh, the decision that you would make is the same. We can see that the p-value for the uh, parametric bootstrap is higher. Right? This is what we mean by conservative. So this is a little bit more accurate per se. And so what one might do now, where you might run into trouble is, in physics and other areas where they use very small alpha levels, this might be concerning, sort of what decision do you make? But in our area, we're using this sort of nominal alpha 0.05, even alpha 0.01. Both situations would lead you to reject the null hypothesis and again, the null hypothesis is that we don't need the random slope. So both of these things suggest that, there is sufficient variation in the slopes to keep that in the model. And we can see that here, right? That, sort of on average, so this is again our kind of pooled or weighted average slope across people, which is as each day goes to the next, we might expect approximately a 10 millisecond jump in reaction time. This is telling us that that is possibly in the range of plus or minus 6 milliseconds. That's again mean slope, standard deviation of the slope, mean intercept, standard deviation of the intercept. Right? We can also see that the correlation between intercepted slopes is small, and that's good. That just means that there's room to grow. So it didn't really matter where people started in terms of the reaction time. Pretty much everybody's increasing. A lot of times when you're looking at like learning or like pre versus post, or you've got like 4 measurements where you're asking people questions with the kind of a ceiling. So, they can't go any higher than, 100% or 7 out of 7. You can see, so that happens a lot in education or anything where you're using a PRO where people start high. They don't have any place to go. And so you'll get a high correlation. You'll get a number close to 1 here. Or actually sometimes -1, meaning that the higher the intercept, the smaller the slope, right? Because you start high, and so you can't go any higher, so your slope is flatter. Whereas if you start low, you can gain, and so your slope's going to be much larger. We'll see that for homework too. Okay. So one more thing. Another thing we might like to try, and we see this, and there's other ways to do this. This is kind of, again, an older approach to trying to model some of the nonlinearity in here. As we can see, there's a couple of people who kind of go up and come back down. We have, again, a sort of this exponential relationship here. We have some maybe crude U-shaped things going on there. So we don't have to fit a nonlinear model. Instead, what we can do is we can try to assess how much of that quadratic trend is really in there and isn't noise. And so to do that, we just add a second predictor where we take our time variable at whatever lag we've used it at, and we square it. So in this data set, simply what we do is we use we take the day of the study and we square it and get days squared. So just to show you what that might look like, I'll load all the data. All the way down here. Okay, so boom. So what does that look like, right? Days is 0 to 9, and so days squared is 0 to 81. And so that might look funny, but with these two predictors together, we're able to model some nonlinearity. So we can fit that model. There's a couple ways to do that. We could add a squared predictor to our data set, or we could use, so here I'll just show you the difference. So get rid of that. If we wanted to, if we didn't want to get ourselves confused, we have this new variable. It's our quadratic version of days, and we fit the model. We can also do that within our function call. It's better to do this one if you've got a lag. So we don't have a lag in our data set, so it's okay to do this. What are we doing? The I is for identity matrix. It's just a way, if we didn't have that in there, the code would get all screwed up. So we kind of make a matrix inside our data set. So just ignore that part. If this makes more sense to you, this is how you can do it. Just to show you, right? They yield the same results. So summary mod days squared. Same thing, right? Because indeed the same numbers are going into it. We can compare this to our random slope model, which would be a fixed effects test. Now, most people don't recommend you use ANOVA at all for this, but we're going to do it. So I'll just do it down here. Oops, I didn't fit that model, so I should do that. There we go. So this is what's called anti-conservative. It's sort of liberal. So this is kind of goes in the opposite direction. In fact, this p-value might actually be too high. And so, or excuse me, it might actually be too low. And so in this case, because it's already over our threshold, this result might actually hold for us. Another way to test that is, again, to do permutation. This is going to take a hot second just to show you how long. So don't get upset if the PB mod comp takes a long time. Literally what's happening in this model is that the models are fit 1,000 different times in many different ways. They're compared, the likelihood ratio test is performed, and we get a p-value. So here we can see that we're actually in good shape. So the parametric bootstrap agrees quite well with the likelihood ratio test in this case. The main reason for that is because we have balanced data. So with a nice balanced data set with a well-behaved outcome and not too many fixed effects or random effects in our model, the naive likelihood ratio test is well approximated by a chi-square distribution. So the p-value from likelihood ratio test is pretty accurate in this case compared against the bootstrap version of it. So in both of these cases, we really don't have evidence that the quadratic effect adds very much. So if I was building my model and I want it to be accurate, I would drop it. I would say, okay, yeah, there is that nonlinearity. I see it here, but there's not enough of it to suggest it's not just some noise. A linear trend generally fits pretty well to each person. All right, so let's summarize what we've done. Again, we can look at some of these. Again, you can get bootstrap confidence intervals. Again, I'll show you that does take a little bit of time too. This model isn't too complex, but it will take some time, so just watch how long it takes. Again, what is a bootstrap? It's resampling. We have to fit the model over and over and over and over and over again. So it's actually pretty quick because this is a simple model. You will find if you use parametric bootstrapping for confidence intervals, it can take quite a long time, especially if you have a lot of fixed effects. The more complex the model is, the more computations that have to be drawn. It also can take a very long time if you have a large data set. So there are some better packages for that I'll discuss later in these tutorials if your data are very, very big. Now, for ordinary linear regression, so numeric outcome that's pretty well behaved, lme4 and this method works quite well with very, very large data sets. The issue is when we turn to logistic regression. There are some newer options. Oakley dokley. I'll let you read this. I put this in here because R has sometimes when you use quadratic terms in a linear model, the linear and quadratic terms can be very, very highly correlated such that collinearity becomes a problem. And so sometimes people, if they're not too interested, like let's say we wanted to just account for time, but we didn't really care about it. We had some stuff at the participant level we cared about. We might use what's called an orthogonal polynomial contrast for time. And all that does is if you use this poly function 2 for a quadratic, it just makes you two new variables. And these two new variables are linear time and quadratic time, but they're orthogonal to each other. So as you can see here, we've got two vectors of numbers. They don't make a whole lot of sense. The effect that this has on the model is essentially nothing in terms of the fit, but you'll get very different terms in your model. In this case, it actually changes the fixed effects quite a bit. So when you use orthogonal polynomial contrasts, we get a much larger quadratic effect. We get really not a lot of evidence for the linear effect. And that's, again, just a function of the fact that now we've got two slightly different predictors. So unless you have a pretty good reason for using those, if you're really interested in time trends, you kind of want to avoid it, but they're there. Okay, so what do? We fit some models with the linear affected days on reaction time. We asked whether there was significant variation in the intercepts and the slopes. And again, significant, we use a grain of salt. The likelihood ratio tests are only approximate. So we kind of use a constellation of evidence from the likelihood ratio tests maybe a bootstrap version, and also looking at the confidence intervals to make that. Right? We also looked at whether the fixed effect of time and whether a quadratic effect, in addition to that fixed effect, um, were significant, and we found pretty good evidence that we should have that linear effect of time, but that quadratic effect didn't really add too much. So here's what we get if we fit both an ordinary linear regression model, that's the dotted line, as well as a low S, so something that it's a local non-parametric fit, fit that too. And we can see, right, they almost look like parallel or overlapping lines, even with allowing, so the low S non-parametric regression is like the most flexible we can do here. And we would expect that if there really was a lot of nonlinear relationships going on here, that we'd see these gray lines being really wavy. They're not, right? It looks like in every case, the linear approximation is pretty good. Again, we do have some nonlinearity, but that may just be some noisiness. Here's this two people here with those kind of weirdness there. So we might again look at all this evidence together and say, reaction time generally can be approximated as a linear function of days. Right? So that's at the very technical mathematical level. At the conceptual level, this is showing us that, yeah, if you deprive people of sleep for a number of days and you test their reaction time, cognition, and this would be, obviously relevant to, working in a machine shop, driving your car, and as your level of, and again, if you dig into the study, they didn't make them stay up all night. Basically, they woke them up a bunch of times. They had people sleep in a lab, woke them up a bunch of times during the night so that they kind of interrupted their sleep. And as the days went on, on average, pretty much everybody's reaction time deteriorated, some people more than others. All right, so your assignment this week is it comes from the John Fox book that I love, and it's a study that he performed with some colleagues where they had histories of a patient group of teenage girls hospitalized for eating disorders, and then 93 comparable control subjects. And I don't know if those subjects were also hospitalized, but not for eating disorders. That would kind of be the best control group there, but we'll put that aside. At the time of data collection, the girls and their parents were interviewed, and based on those interviews, an estimate of the average number of hours per week of exercise was constructed at each girl's current age, which varied from girl to girl, right, in at most 2-year intervals, and then at most 2 years intervals into the past, starting at age 8, or really going back to age 8. Right? So that's a mouthful. So what does that leave us with? It basically leaves us with an unequal number, and you can see here, right, that for each group of the control group who don't have an eating disorder and the patients who are hospitalized for eating disorders, as they go back into the past, there's an unequal number of observations at each time. That's totally okay. Right? What the assignment's going to be about is to see what happens when, so we don't have a natural 0 point in our model. So we could make 0 age 8 for all the girls. We could put it somewhere in the middle, the average age for the girl, or we could put it at the end of the study. And so you're going to play around with that. Just to take a look at, there's too many people in this study. As you can see, if we add together 138 and 93, we've got a lot. Was that about 220, 230 girls? So here I've just sampled 20 of them and plotted the sort of estimated number of hours of exercise per week, what you're going to see is that the girls with eating disorders tended to exercise a lot more. The flat lines tend to be the control group. And so we're going to do some similar stuff next week. So the important thing to note is that in your code for next week, there's going to be, or for over this week, the homework, which will be discussed next week, there's two additional age variables. One where the lag, the L in the formula way back up here, is going to be the end of the study. So they're the maximum age of the girl. And then another one in the middle. So when the girl was at essentially the midpoint of the study, and you're going to do some stuff and see what happens to the model output when you change the way the age is represented. Okay? All right, so get to it, and we'll see you back next week.